Take a look at an example problem with um, a moving charge and a magnetic field. And we're going to make this one pretty straightforward, but it illustrates a lot of conceptual things. So let's just imagine we have some region of magnetic field. And here we are. Now, just as a heads up, you guys know that when we moved on to circuits, although a drawing is still helpful and maybe even essential, it becomes less important that we have coordinate systems associated with a circuit. Everything's constrained to move on the path of the conductors, so you don't really need a coordinate system. That's changing now. We're going back and we need some vectors again, so just remember that as you're looking at these problems. So, for example, let's say I've got a charge, and this is what we did in class. I'm going to do it in a little more detail, and I'm going to correct an error I made in class as well. So let's say we've got some V0 here, and there we go. Let's leave it at that. Okay, so there's our drawing. Now we need to have a coordinate system. So I'm just going to go ahead and set up the coordinate system like this. Let's call this X. And let's call this Y. It did occur to me as I was thinking about doing this video that you guys might not remember the importance of a properly constructed coordinate system. And I do not mean right now selecting the origin or the orientation of the X and Y. What I mean is selecting the orientation of the Z. We're doing all these things with right-hand rules, and we haven't talked about in these videos yet, but we've talked about it in class. We're doing a lot of things with right-hand rules. Right-hand rules only work if you set up your coordinate system in the proper way as well, which is as a right-handed coordinate system. So it is important to remember as your particular case is coming right towards me this way. Is that going to translate on this video? I hope it does. Anyway. So X, Y, Z is going this way, back towards the back wall of our Posh Physics 262 studios. Okay, and that's just for you, Sean. Okay, let's see, where are we? Oh, okay, so now, here's what we know. We know we have, all our givens are here. Charge, velocity, a magnetic field. Actually, I haven't written the magnitude, so write that magnitude. And you'll notice these are vectors, and the reason that's important is because you will recall the Lorentz force is equal to Q V cross B. All right, so now, I told you there are a couple ways to do this. So the first way is to just look at the right-hand rule. So our V0, I put my fingers in the direction of QV. Okay, so there it is. QV is going that way. Then I take I put my whole hand in that direction, which of course includes my fingers. Then I turn my fingers to where they're in the direction of the B field. In this case, that happens to be into the glass. Okay, so now I have a B that's going into the glass. I have a V that's going this way, and my thumb is pointing upwards. Therefore, my force is upwards, except that's what V cross B is. V cross B is upwards. But what is this Q? This Q is the charge of an electron, which is negative. Therefore, my force is actually going to be down, and that's what I forgot to do in class when we briefly went over this. So my force is actually going to be in this direction. Okay, and what's its magnitude? Well, VB sine theta is the magnitude, and you guys will recall that, and we set it up in such a way that this has 90 degrees between the velocity and the magnetic field. Sine of 90 is 1, so it's just VB. So this is EVB, where E is just the magnitude of the electronic charge. Okay, so now let's look at this in just a little bit more detail. So that's what we're expecting this to be. But now let's go ahead and say, can't we look at this in some more rigorous fashion than just this funky little right-hand rule? And the right-hand rule serves us well, but we need to know that it can serve us well. So I'm going to redo my coordinate system here just so we see everything. So what do we have? My v0 as a vector is equal, oh, I'm sorry, my v as a vector is equal to v0 x hat. You'll see, there it is, here's my x. Oh, I didn't need that hat. There's my x. Okay, what is my b? Well, my b is equal to minus b0 z hat. You'll recall z was coming, as a matter of fact, I'll just redraw it. Z is coming out this way, so it is in the negative z direction. And I'm going to go ahead and change this to the IJK notation. So you guys, I believe, are all going to be comfortable with that. So this is minus B0K hat. Okay? All right. So now, how do we do a cross product when we want to actually write it out and do the more formal calculation? Well, the cross product, V cross B, is just this. It's just I, J, K, and then it's V, B. All right, well, as a matter of fact, I'll go ahead and write it out. It's just VX, Vy, VZ, BX, BY, BZ. All right. And this will be just the determinant of this. But you'll see what we have here. We have V is just V0x, so we have no Vy, we have no Vz. How about B? B is just in the Z direction. It's just a B. So what we have is a V0 and a B0, and then everything else here are zeros. So that's just substituting in the value that we actually have. So you'll recall there are all sorts of different ways to do this, and if you memorize the permutation way, that's fantastic. I always have to look that up when I do it that way, but I can kind of remember the geometrical way where you go this way down diagonal, this way, so it's plus this minus this. Then you move over here and say it's plus this minus this. Then it's plus this minus this. Okay? But you'll notice there's lots of zeros in here. So the only term that's going to give us anything is as we go in this direction and multiply j hat, v0, b0. Oops, I made a mistake. This is a minus b0 here. Okay, so that's the only term that's going to give us anything. It's a minus b0, v0 in the j hat direction. However, this is the minus side of doing this determinant because we're not going in this direction, we're going this direction, so it's a minus side of that. So we actually have a negative of negative v0, b0, j hat. So, of course, that just leaves us v0, b0, j hat. Except, this is not our force, this is just v cross b. Now we're going to take that charge and put it in here again, and what do we have? Our charge, which I erased, is going to be equal, it's negative E, where E is just 1.602 times 10 to the minus 19 coulomb, just the charge on an electron, so, or the magnitude of the charge on the electron. So that is negative, so what does that mean we have? It means our force is minus E V0, B0 in the j hat direction. All right, and this is our Lorentz force. Well, now let's look at what we had up here earlier. We used our right-hand rule to say, okay, QV cross B goes like this, but it's negative, so it's this way, so that is the minus j hat. And what direction are we going in? Minus j hat. So you'll see that our results here are consistent, and really this is just a way of saying the right-hand rule is a convenient way of doing this. Sometimes you'll want to actually work this out, especially if you're not certain of your results with the right-hand rule, as long as you're, I know you guys are going to think this is funny coming from me, as long as you're careful with the minus signs, then you'll be fine. Okay, that's a quick introduction into into calculating the Lorentz force.